Hi, in this video, I'm going to go through the A-level, the AQA A-level chemistry paper. This is paper 3. This is the 2021 paper. And I'll just do the first half of the paper in this video and continue it in the second one. Okay. All right. First question is about ethane dioic acid and its ion, the ethane dioate ion. Ethane dioic acid reacts with propane 1,3-diol to form a polyester. Draw the repeating unit of the polyester. Okay, so let's draw ethane dioic acid first of all. And then we'll draw the other monomer, which is propane 1,3-diol. Okay, so what's going to happen is we are going to lose that water molecule there. Get rid of that and form a new bond between the carbon and the oxygen. So I'll just tidy that up. So we formed a new bond there on the long side. Right, now that's going to happen at the other end as well. So if I get rid of that, you're also going to have the same thing there. So on. And at this end, the ethane dioate molecule, yeah, that's going to be connected to a, okay, now I've drawn more than a repeating unit. So let's start off there. And we keep going until we repeat the thing. So we need to go all the way up to there. Make sure that bond comes out of the bracket there. Let me insist on that. And then we'll rub out all these extra bits here. Okay, so that is the repeating unit. I like to draw more than one repeating unit sometimes, and then rub out the extra bits just to make sure you've got it right. Okay. Of course, in a repeating unit, you mustn't draw the same thing twice. Okay, let's move on. Explain why polyesters are biodegradable, but polyalkanes are not biodegradable. 2 marks. Right, I'm going to just go to that diagram. The reason why these are biodegradable because you've got a polar. You look at the marks, you know, basically it's because you've got a polar bond here between the carbon and the oxygen. So you're going to have a partial positive charge on. For 1 mark, that's all you need to say. You've got a polar bond in that. Whereas in the polyalkene, all you've got is a load of carbon bonds, and they are not polar, so there's no nucleophiles can attack anywhere there. I'd say for 1 mark, I think you just need to mention the polar bond. Of course, what will happen is, and you don't have to say this in your answer, is nucleophiles like OH minus can then attack that carbon and break one of the bonds in the chain. So 2 marks for that. Okay. Sodium ethane dioate is used to find the concentration of solutions of manganate in solution by titration. So you've got manganate there reacting with the ethane dioate ion, 2:5 ratio. Okay, so we've got to calculate the concentration of the potassium manganate solution. Okay, so what have they done here? They make up a standard solution of ethane dioate, 250 centimeters cubed. All right, so that's the sodium. It's the dioate ion, not the not the acid. Take 25 of that out into a conical flask, and they're going to titrate that against the manganate solution. Yeah, that's going to run into the into the flask there. Okay, so let's work out then. So they tell us we've got 0.162 milligrams of sodium ethane diorite there. So let's work out the number of moles of that. So moles is equal to mass over mR. The mass is 162 milligrams, so that's 0.162 grams. And the MR, they tell us, is 134. So that works out to be 1.208 times 10 to the minus 3. Moles, and that is in 250 in here. But we don't take 250, we're not in the titration, we only take 25 out. So we're going to say this, so the moles in 25 centimeters cubed is going to be a tenth of that, so divide by 10, because we're only taking 25 of 250 out. So that's going to be equal to 1.208 times 10 to the minus 4 moles of the ethane diorite ion. Now, the equation tells us that they react in a 2:5 ratio. Look here, 2 moles of manganate with 5 moles of ethane diorite. So now we need to take that into account. So, so we're going to say, right, the moles of the manganate then. And that is going to be in the titer value, which is 23.85. That's going to be 1.208 times 10 to the minus 4. Now it's a 2:5 ratio, so we're going to multiply it by 2/5. That gives us 4.836 times 10 to the minus 5. Moles of manganate. Look what volume that's in. That's in a volume of 23.85. We need to work out the concentration of the potassium permanganate. So we do moles divided by volume. So let's do that. Concentration of manganate. Moles of a vol. 4.836 times 10 to the minus 5 divided by this, and that's going to be in dm cubed, so that's going to be 0.02385. Got to divide it by 1,000 to put the centimeters cubed into dm cubed. We do that, we get a value of 2.03 times 10 to the minus, it's actually 2.028 times 10 to the minus 3, but we want to give our answer to 3 significant figures. So 2.03 times 10 to the minus 3 moles per decimeter cubed, which is about common sense answer. That's about the right answer. When you do manganate titrations, you usually use a concentration of, which seems very low, but that is the concentration, 0.02 moles per decimeter cubed. Manganate is a very strongly colored, even at those sort of concentrations, it's very, very dark. Okay, so here's a question about practical. This paper, of course, paper 3 is with an emphasis on the practical work. We've got a 25 centimeter cube pipette. On figure 1, draw the meniscus of the solution when the pipette is ready to transfer. So I'm going to draw it there, so a bit small. So I'm going to draw it nice and big here. Okay, right, there's your mark, and you want your meniscus, right, to be, it's going to be like that. Put it in a different color. Just the bottom of the meniscus touching the mark line. That's what you want for 1 mark. That's the correct answer. Potassium manganate is oxidizing and harmful. Sodium ethane diorite is toxic. Suggest safety precautions other than eye protection that should be taken when filling the burette with potassium manganate. Right. Sensible thing is to fill it at eye level. So take it out of the stand and fill it up rather than standing on a chair, whatever. So fill at eye level. And then the other precaution, when you're dissolving the sodium methane dioate in water, well, that's toxic. So you can say either wear gloves, or probably what you would actually do is just avoid spillages. And if you do spill it, avoid spilling the solid on your skin. And if you do spill it on your skin, wash with a lot of water. Okay, state the color change seen at the endpoint of each titration. Well, I've drawn the equation there again. This stuff here is purple, and this is more or less colorless. It's very, very pale pink. It's more or less colorless. Everything else is colorless. Okay, so the endpoint, the change you're going to get is, right, you're going to run purple stuff into that flask. It's going to disappear as it turns into Mn2 plus until you reach the endpoint when all of that is run out, and then the purple color will persist. Okay, but you don't want to add enough so that it actually looks purple. You just want to add a tiny, the smallest excess amount. So you want the first permanent pink tinge to the solution. I'll say something like that. Okay. Well, that's actually the only essence of the color change. Forget about the permanent pink tinge, very pale pink. Okay, figure 2 shows a burette containing the manganate solution. Give 2 practical steps needed before recording the initial burette reading. So that's before you start running any. There's 2 things you've got to do. You should take the funnel out, remove that funnel. And the other thing is, if you look around there, you've obviously got air in the jet. So you need to remove the air bubbles by running some solution through. So remove the funnel and get rid of the air bubbles in the jet space. 2 marks are fairly standard things to do during a titration. Okay, so this is about ethane dioate ions acting as ligands now. Okay, so we've got this complex ion, the iron 3+ with 6 water ligands. All 6 water ligands are replaced by ethane dioate ions. Okay, explain why the replacement of the water ligands by ethane dioate ions is favorable. Okay, so first of all, let's just talk about ethane dioate ions. Well, they are bidentate ligands. That's pretty important to realize that. Okay, so you got oxygen with the negative charge, that one, and you can, so that can form a dative bond and that can form a dative bond. It's a dative, sorry, it's a bidentate ligand. All right, explain why the replacement of the water ligands is favorable. And we've got to talk about enthalpy, entropy, and the free energy change. That's what we've got to talk about. Okay, so this is, of course, we are referring here to the so-called chelate effect, where if you use a bidentate or a polydentate ligand, the reaction tends to only really happen in the forward reaction. And the complex is irreversible. You can't replace the bidentate ligands with water molecules. So let's see why. Let's write down the equation. Okay, so we're going to write down an equation first of all. So we start off with Fe H2O 6 3+. Now, because this is bidentate, the ethane dioate, we only need 3 of these ligands to form 6 dated bonds. So we want 3 of those. Right, when they replace all the water ligands, you're going to have that. 3 of those. What's the charge on that going to be? Well, it's going to be 2-, isn't it? Because you've got a total of 6-, because each ethane dioate iron's got 2- charge, and that is a +3. So that's going to be 3- is the charge on the iron. And don't forget what happens to all those water molecules that were ligands, they come off. Okay, 6 of them, and that's really important. Okay. Now, let's talk about the entropy change here before we talk about enthalpy. So, well, we can see that the entropy change, delta S, is going to be positive. Why is it positive? Well, if we look on this side of the equation, we have got 4 species in aqueous solution, whereas on this side we have got 7 species in aqueous solution. So because you've got more, you've increased the number of species in aqueous solution, you've increased the disorder, okay? So entropy is positive here. And that's what's going to drive the whole thing forward here, we'll see in a minute. Now let's talk about the enthalpy change now. Now the enthalpy change for most ligand exchange reactions is going to be approximately 0. There's not very exo or endothermic. And why is that? Well, as you can say you've broken 6 dated bonds to the ion, but then you've formed 6 new ones. Breaking bonds is obviously endothermic, making bonds exothermic, so overall it's about 0. Now we talk about how this is going to influence the free energy change for the reaction. Right, okay. Why is this? So we've got to see why is it favorable. We look at delta G is equal to delta H minus T delta S. Right, we know that this is approximately 0. T, the absolute temperature, can only have positive values. So that means this whole thing here, minus T delta S, because delta S is positive. That whole thing, that delta S is positive. So this whole thing in the bracket there, the circle I've drawn, is negative. So that is going to make delta G negative. That means the forward reaction is thermodynamically favorable possible. Of course, the backward reaction, delta G would be positive and it would be unfavorable. So that is called the so-called chelate effect. And so you need to know about that. It's a fairly standard question with a bidentate ligand in that case, sometimes with a polydentate ligand like EDTA, which can form 6 dated bonds. Okay, question 2 now. This is about a protein, fibrin, which can be broken down into amino acids using an enzyme. A student uses TLC, thin layer chromatography, to identify the amino acids. The student identifies 2 of the amino acids as alanine and serine. Use figure 3 to calculate the RF value and show your working. Well, I am not actually going to calculate it because I can't measure on a computer screen. But let's just show what we're going to do. And you've got to identify the acid. So RF value is equal to the distance traveled by the spot from the spot divided by the distance of the solvent front. So that's how you work out an RF value for this. Okay. So use figure to calculate the RF value of the unknown one. Okay, so the unknown one, I was going to do it roughly. I am going to say, right, that distance is about, so the distance of the solvent front, let's say that is about 10. And the unknown, well, it's about a third of the way up, isn't it? So that's going to be equal to about 3. That's used on 3 units there. So the RF value, you'd obviously do it with a ruler and measure in millimeters. I'm not going to do that. Is going to be 3 over 10 is equal to 0.3 approximately. And you can see glycine is the only one there with a value of 0.3. So the unidentified amino acid is glycine. The amino acids can't be seen as they move during the experiment. State how the amino acids can be made visible at the end experiment. Well, the usual thing is to treat them, spray with a chemical called ninhydrin. which forms reacts with amino acids to form a colored compound that you can see. That's what I would say in hydrogen. The other thing you can do is look at it under UV light, and amino acids absorb in the UV part of the spectrum, and so you can visualize them there. So either of those two methods is okay. Right. State why each amino acid has a different RF value. Well, they move different amounts up the paper. Why is that? It's because they have different affinities for the paper, which is the stationary phase, not the paper, it's TLC plate, the stationary phase, the silica gel, and the solvent. So each amino acid have a slightly different liking or affinity for those two things, and so they move different amounts. That's all you need to say for 1 mark. Of course, if it's got a strong affinity for the solvent, in other words, can it form a lot of intermolecular forces with the solvent, it's going to move fairly high up with the solvent and give you a big RF value. But if it's not forming that many intermolecular forces with the solvent, it won't trouble so far. Okay, question 3 about ketones. Okay, solution X reacts with liquid ketones to form a crystalline solid. Okay, the reaction can be used to identify a ketone if the crystalline solid is separated, purified by recrystallization, and then melting point determined. But this isn't on the AQA syllabus, but it's on other ones, and it's sometimes called Brady's reagent, this stuff, and they use it. And contains a chemical called 2,4-DM dinitrophenylhydrazine. Don't need to know that. That forms an orange compound, and depending on the ketone, the orange compound will have a slightly different melting point, and you can identify it. That's the background to this. But all we're asking here is, how is the solid crystalline, is that separated and purified? Well, it's going to be purified by recrystallization. 5 marks here. So what are the essential points to recrystallization? Well, the first thing you need to do, it relies on the fact that things tend to be a lot more soluble in hot solvents than in cold solvents. So what you do is first of all, you dissolve the solid in the minimum volume of hot solvent. Okay, that's really important that you say both those things. You say minimum volume and you say hot. Okay, so you're going to form a saturated solution there at high temperature, and then you are going to cool the solvent, the solution. Okay, now the solid will be less soluble when the solvent's cold. So most of the solid will precipitate out, will crystallize out. Some of it won't, some of it will, a small amount will remain in solution in the cold solvent. You lose that, but that can't be helped. The solid will crystallize out. How do you get rid of the solid? Well, you filter it with a vacuum filter under reduced pressure. Probably worthwhile mentioning that will be in a Buckner funnel. And then finally, what you should do before you just dry that, you should then wash those crystals to remove soluble impurities. Wash with cold solvent, small amount of cold solvent. And then you should leave it to dry. That is the complete recrystallization method. Doesn't actually ask you to explain it, just say how you do it. So all those bullet points there would get you 5 marks. Propanone reacts with the weak acid HCN to form hydroxynitrile. The hydroxynitrile is usually made by the reaction of propanone with KCN, followed by dilute acid rather than with HCN. Okay, what's the hazard associated with the use of KCN? Right, KCN is toxic. cyanide, potassium cyanide is very poisonous. That's all you have to say. I suggest a reason other than safety why KCN is used instead of HCN. Though, of course, the reason why you wouldn't use HCN or avoid it is because KCN is a solid, so that's as long as you don't swallow it, it's okay. Whereas HCN is a gas, so it'd be very difficult. You have to do it in a fume cupboard and avoid breathing it in. But if there's a reason other than safety, why would you use KCN? Right, the reason why is because HCN, like that, is a weak acid. It's a very weak acid. So the concentration of the cyanide ion will be very low. So you need quite a bit of cyanide ion because that is the nucleophile which attacks the carbon-carbon. In your ketone. Okay, so there's your carbon-carbon, the one with the delta positive on it, and you need the cyanide, right? That's a nucleophile, and so because it's a weak acid, the concentration of that is very low. So you need to add KCN. Okay, now we've got the mechanism for the reaction of propanone with KCN followed by dilute acid. Okay, so this is pretty standard. This is, of course, a nucleophilic addition. Usually they ask you for the name of that. They haven't asked for it in this time. Okay, so here's our propanone. Cyanide ion, where we've got the lone pair on the carbon, negatively charged. First movement is that pair of electrons attacks the delta positive carbon atom there. And then the pi bond breaks, we show that pair of curly arrows going there. And we're going to end up with this intermediate now. We've got O minus. The cyanide group is now attached. Make sure that line's going to the carbon because it's forming a bond to the carbon, not the nitrogen. And we've got CH3. Now you have to add the dilute acid now because the last thing is for this to be protonated. So you can just draw an H plus ion, that's fine. So the pair of arrows, you must draw a lone pair on the oxygen. And the lone pair goes from the lone pair onto the hydrogen, and you form the hydroxynitrile. That now becomes an OH. Okay, that's that mechanism. Okay, on to group 7 chemistry now. Okay, give an equation for the reaction of solid sodium bromide with concentrated sulfuric acid to form bromine. Now you have to remember here, well, this is a redox reaction. The bromide ion isn't a terribly good reducing agent, and it can only reduce the sulfuric acid to SO2. Okay, you may remember the iodide ion can reduce it right down to H2S or to solve for the element. Okay, so before writing this equation, the way I would do it is just construct two half equations, add them together, and that way you're thinking logically and you're not just remembering things. Okay, so the bromide ion, right, that gets oxidized to Br2. We need to put a 2 there to balance that. We want 2 electrons there. The H2SO4, the conc sulfuric acid, is going to get reduced to SO2. So I need to balance that half equation. So I need to balance for oxygens. I've got 4 oxygens on the left, 2 on the right. So I want 2 H2O there. I've now got balance of protons. For hydrogens, I've got 2 hydrogens on the left, 4 on the right. So I need 2 H plus there. They'll come from the sulfuric acid, of course. Now, finally, I need to balance for charge. I have got plus 2 on the left of that half equation and 0 on the right. So I need to add 2 electrons in there. Now, I can combine these two half equations to a full equation. I don't need to multiply out anything because they've both got 2 electrons. So simply the reaction will be 2Br minus plus H2SO4 plus 2H plus goes to Br2, SO2, and H2O. Now, if you look in the mark scheme, that's perfectly acceptable to write an ionic equation. That's probably what I would write. It's simpler. If you wanted to write a full equation, well, what are the spectator ions there? It's potassium ions. What are the spectator ions there? It's sulfate ions. So you'd write down just I wouldn't bother writing it, but right, 2 kBr, and then you'd want 2 sulfuric acids now. Another sulfuric acid, another sulfate ion for that one. And that's going to go to Br2, SO2, H2O. And what happens to those spectator ions? Well, the K plus ions and one of the sulfates from the sulfuric acid, that's going to form K potassium sulfate, K2SO4. So if you don't like ionic equations, that's the answer there. But ionic is fine. One observation made during this reaction. Okay, well, the only right answer really is to say that, right, you're going to get, because you're forming bromine, you will see a brown vapor. It's quite exothermic, so you don't tend to see the liquid. The brown vapor is formed during the reaction. So you're adding drops of conch sulfuric acid to white potassium bromide solid, and it sort of turns brown, gives off a brown vapor. Okay, more on the halides then. Right, a solution that's thought to contain chloride ions and iodide ions is tested. Okay, right, so it tells you what they do. Give you a reason for the use of each reagent here. So what they're doing are adding silver nitrate. So basically, when you add silver nitrate, the chloride ions are going to give you AgCl solid. That's a precipitate, and that's going to be white. That will redissolve in ammonia. That will dissolve in dilute ammonia. Because you've got chloride ions and iodide ions, well, you're going to get AgI forming there, solid as well, and that's yellow. It's a yellow precipitate, and that won't dissolve even conch ammonia. Okay, it won't redissolve. So I basically very quickly explain the observations there. Right, let's do this. Okay, so let's see what it says. Give the use of each reagent. Right, why are we acidifying nitric acid first? Well, the reason why you need to add nitric acid is to remove any hydrogen carbonate ions or carbonate ions or OH minus ions, because they would all interfere with the test. The reason why they'd interfere is because you'd form insoluble sodium compounds from them. Sodium, silver. So silver hydrogen carbonate, silver hydroxide, they're all insoluble. That would mess with the test. Right, why are we adding silver nitrate to the solution? Right, because we're adding silver nitrate to react with the chloride ions to form AgCl solid and the iodide ions to form AgI. Okay, why are we adding dilute aqueous ammonia? Well, the reason why we're adding that is because the silver chloride will dissolve in dilute aqueous ammonia, whereas the silver iodide, the yellow one, will not dissolve in it. Okay. Right. So let's see what is going to happen there. Okay. So explain the observations. Right. So what we're going to see first of all is you'll get a mixture of a white and a yellow precipitate, so it's going to go cream. Then when you add the NH3, the yellow precipitate will redissolve, and so that the precipitate will become thinner, and it will lose some of its yellow color and become, say that again. So you get the white and yellow precipitate, which is cream. Add the ammonia, the white precipitate will redissolve, but the yellow one won't. So you're going to lose some of the whitish color. It's going to become darker yellow, but the precipitate will become a bit thinner because there's less of it. Right. Ionic equations for any of the reactions. So we need the reactions occurring at Ag plus Cl minus goes to AgCl. And also Ag plus and I minus goes to AgI. And now we need to write an ionic equation for the silver chloride dissolving in ammonia. How do we write that one down? Well, we have to remember we've got AgCl plus ammonia. I have to remember that silver is unusual. It usually forms ligands. It's got a coordination number of 2, and it has 2 ligands for each silver ion rather than 6, which is the usual number. So you're going to get AgNH3. There's 2 of those. That's the complex ion, and that's soluble. So that's going to have, a positive charge on it. Okay, and what's going to be left over are chloride ions floating around the solution. You need to balance that, so we need 2 NH3s there. Okay, so that is the other ionic equation that you need there. And that will do it for 5 marks, I think. Okay, we've got a question about buffers here now. Okay, right, so we've got a mixture of methanoic acid, let's call that HA, and sodium methanoate, so Na plus A minus, in aqueous solution acts as an acidic buffer. There's the dissociation, right? So we can write that as HA goes to A minus plus H plus. Okay, calculate the mass in grams of sodium methanoate that must be added to that much methanoic acid to produce a buffer solution with that pH. This is a buffer calculation. So what I would always do is, don't forget the Ka expression is A minus H plus conc over HA. Whenever I do a buffer calculation, I always rearrange to get H plus, make that the subject there. Okay, so we're going to, actually, I'm going to do it in the bottom over here, sorry. Okay, so we're going to have H plus concentration is equal to Ka HA over A minus. Right, now that's the concentration of HA, and of course the concentration of HA is equal to the number of moles of HA divided by the volume V, and the same for A minus. So we're going to substitute that into this equation here, and we're going to cancel out the volume terms there. So we're going to say H plus over Ka is moles, multiplied by moles HA over moles A minus. Right. Divided by V, divided by V. Those V's are going to cancel out. Let's get rid of them. Right. Now I'm going to rearrange that. Now what do we know in this, right? We know H, we can work out H plus because they tell us the pH. We can work out Ka because they tell us the pKa. We can work out the moles of HA because, well, they tell us we've got the volume and the concentration of methanoic acid of the HA. They tell us we can work out that. The only thing we don't know are the moles of A minus. And that's what we want to find out, because we've got to find out the mass of sodium methanoate. Okay, we look at the moles and we can just multiply by the MR and get the mass. So let's rearrange that equation to get moles A minus as the subject. Let's do that. If you do that, you end up with Ka over H plus multiplied by moles, multiplication side, sign HA. Right, now let's work out the moles of HA. Is equal to concentration times volume. rub some of this out here. Okay, concentration, we have got 0.1 and we've got 25 centimeters cubed. So that's 0.1 multiplied by 25 over 1,000, 0.025, convert to dm cubed. That's 2.5 times 10 to the minus 3 moles. Right, now let's do H plus concentration. Well, that's equal to the pH, 10 to the power of minus pH, isn't it? And let's work out the Ka. Well, that's equal to 10 to the power of minus pKa. They give us the pKa value. So let's put those numbers into this equation here, moles A minus. So moles A minus is Ka. So that's Ka is 10 to the minus pKa, so that's 10 to the power of minus 3.75 divided by the pH, sorry, the H plus concentration, that's 10 to the power of minus pH. The pH of the buffer, they tell us is 4.05. Okay, so we've got that. And the moles of HA, we worked out there, 2.5 times 10 to the minus 3. So do all that on our calculator. And we get moles A minus is equal to 4.988 times 10 to the minus 3. Okay, so now we have got the moles of A minus, so that's the moles of sodium methanoate. That's the moles of that. And of course, the formula of that is NaCO. So we need to work out the MR of that. Well, the MR of sodium, I'm sorry, I'm missing an H off there. Okay, so the MR of that, 23 for the sodium, 1 for the hydrogen, 12, and then 32 for the oxygens. That gives us 68. Let's work out our mass of sodium methanoate then, finally, to get our answer. So mass of sodium methanoate is equal to moles times MR. 4.998 times 10 to the minus 3 multiplied by 68 gives us, so 3 significant figures, it gives us 0.339 grams. And that is the end of that question. Right, now that is as far as I'm going to go with that paper in this video. I'm going to continue with the second half with the multiple choice questions and question 6 in the next video.